Hello, my name is Spencer ACUNA, and today I will be reviewing the atomic spectra and how it serves as evidence for the theory of quantum mechanics. The lesson will go as follows. First, we're going to review the idea of quantization, which serves as the basis behind quantum mechanics. We'll then discuss quantum mechanics and then move in towards spectral lines, which is a general term for atomic spectra. In the literature, they're used interchangeably. So once we understand spectral lines, we will kind of link quantum mechanics to spectral lines as we understand electromagnetic radiation and electron excitation. Lastly, we will review the atomic spectra of hydrogen as an example to solidify our understanding. So, quantization, what does it mean? If something is quantized, it is restricted in the number of possible values of a quantity or states of a system so that certain variables can assume only certain discrete magnitudes. This is the idea behind stairs. Stairs are quantized. You can exist on the first or the second or the third or the fourth and so on steps, but you cannot exist on the 3.56th step. You are either on the third or the fourth. So stairs are restricted in the number of possible values that you can be at. Stairs are quantized. A slope, like which a skateboarder can slide down, is not quantized. The skateboarder can be at the top or at the bottom or anywhere in between. The slope is not restricted in the number of possible values you can be at. So stairs are quantized. A slope is not quantized. So quantization serves as the basis behind quantum mechanics. The theory of quantum mechanics states that electrons are quantized in certain orbitals. Electrons can exist on the first orbital, or the second, or the third, or the fourth, and so on, but they cannot exist in between those different orbitals. The Bohr model of the atom, like the picture on the left, demonstrates this idea. It's normally what we think of when we think of an atom, the nucleus with electrons flowing around it at certain levels. But the theory of quantum mechanics takes it a step farther. They say that these orbitals are also quantums, or a discrete quantity of energy proportional in magnitude to the frequency of the radiation it represents. So, electrons can exist on the first orbital, or the second, or the third, or the fourth, but those orbitals also have discrete energy levels. So the electrons on the first orbital will have an energy level of 1, and the electrons in the second orbital will have an energy level of 2. Because electrons can exist between orbital 1 and orbital 2, they cannot have energy levels that are equal to 1.5 or 1.6. They can only have 1 or 2 or 3 or 4. So electrons in their location or orbitals and energy are quantized. The Bohr model shows this, but it's not exactly accurate in describing where electrons are found. The atomic orbital theory shows this in the picture on the right, that electron orbitals are a little bit more complex, and we're not going to dive into it. These orbitals were discovered using mathematical theories and formulas, but just understand that the Bohr model of the atom isn't exactly accurate in showing where electrons will actually be found. They flow in these orbital clouds, as shown in the right, but the Bohr model of the atom can help us understand the idea of quantized energy states. So let's review the idea of spectral lines or atomic spectra so that we can see how this serves as evidence for the theory of quantum mechanics. Spectral lines are a dark or bright line in an otherwise uniform and continuous spectrum, resulting from emission or absorption of light in a narrow frequency range compared with the nearby frequencies. So we have a continuous spectrum of light. And that continuous spectrum, everything from the red frequencies and wavelengths to the purple, is exposed to an atom. This is what we see when we have that exposure. Certain wavelengths and frequencies are absorbed, while others pass straight through. And then those same frequencies are emitted by the atom. So it's interesting that this is happening. Only certain frequencies, but not the entire spectrum, are absorbed and emitted. This will serve as evidence for the theory of quantum mechanics. In order to link the theory of quantum mechanics to spectral lines, we have to understand electromagnetic radiation. Electromagnetic radiation is everything from radio waves to visible light to gamma rays. It's all the same. You have a photon with different levels of frequency and wavelength, but also different energy levels. Energy is equal to the Planck's constant times frequency, and frequency is equal to the speed of light over wavelength. So we learn that frequency is proportional to energy of the photon, and wavelength is inversely proportional to the energy of a photon. So radio waves have super long wavelengths, and thus don't have a lot of energy. But gamma rays have a lot of energy because they have a higher frequency and lower wavelength. So if we go back to the theory of quantum mechanics, that electrons exist in quantized orbitals and energy states, we remember that a quantum is a discrete quantity of energy proportional in magnitude to the frequency of the radiation it represents. So the energy that electrons have in the first orbital is equal to a certain amount of energy found in a photon, and that photon will have a set frequency or a set wavelength in order to have that amount of energy. So quantum mechanics is explaining what we see with the atomic spectra, why atoms absorb certain frequencies and emit certain frequencies while others pass straight through. Let's walk through what's actually happening with electron excitation. So a photon with a certain energy excites an electron. That electron absorbs the energy of the photon, and it jumps up to a higher energy orbital, a different quantized state. But in this excited state, the electron isn't super stable, so eventually it drops back down to the starting position and releases a photon of energy. The energy equal to the difference of energy level between the first state and the second state. So let's say an atom or an electron has an energy level of 2. When it is exposed to a photon, it can jump up to different orbitals, different energy levels. Let's say it's going to jump up to the excited state, the energy level of 6. If the photon that the electron is receiving would push it up to, let's say, 6.5, it wouldn't get excited because there's no orbital there. Remember, electrons are quantized. They can exist only at certain states. So the energy of the photon, in order to be absorbed, has to equal the energy difference between the starting state and the ending state. Same thing with emission. Say we're on the energy level of 5 and we're dropping back down to the energy level of 2. The photon emitted has to equal the energy difference between state 5 and state 2. It cannot release amount of energy that would drop the electron to the energy level of 1.5 because there's no orbital there. It has to be from 5 to 2, or 5 to 4, or 4 to 3. Because orbitals, energy levels, electrons are quantized. They can only exist at certain states. So let's use hydrogen as an example to solidify our understanding. Hydrogen is exposed to all these different frequencies and wavelengths, and each frequency and wavelength of the photon has a certain discrete energy level. While some wavelengths and frequencies pass straight through, others are absorbed. That's because those amounts of energy and wavelengths and frequencies are the exact same amount of energy needed for an electron to jump up from one orbital, one quantized state, to another. We don't see a whole spectrum being absorbed because electrons don't exist on a slope. They can't be at any point, only at certain energy levels. So because electrons absorb only certain frequency, wavelengths, and energy levels and emit those same frequencies, energy levels, and wavelengths, it shows that quantum mechanics is real. It shows that there are set energy levels that electrons exist at. So atomic spectra supports the theory of quantum mechanics.